Okay, now what we're going to do is we're going to go through and we're going to take a look at the proportions instead. So what I'm going to do is I'm going to go ahead and share that screen, and what we're going to do now is we are going to reevaluate how we did this. So now what's going to happen is the following. On the back side, it's going to say to me, now instead of the count of candies, what we're going to do is we're going to do the proportion of candies. So these were the number of candies I got: 19, 17, 21, 23, and 24. What I'm going to do is turn them into proportions. So how I turn them into proportions is I use this formula: p hat equals x over n. Number of successes, x, over your sample size, n. So my first one is my 19 oranges out of 50, which is 0.38. The next one is my 17 oranges out of 50.34, and all the way through 21 out of 50.42, 23 out of 50.46, 24 out of 50.48. Now, the big thing I want you to notice is how I put that proportion there, that fraction to show the decimal. You got to do that. That's how we show work. That's how we show work. Okay, now, sketching the dot plot. The dot plot is, oddly enough, going to look like this, and I'll show you again where we are. So before, what we had is we had this count. I did it 1,000 times. And notice the count down here goes 9, 12, 15, 18, 21, 24, 27, 30, 33. Well, what I'm going to do is I'm going to flip it over to proportions. What that tells me now is the following. Notice it changed the 9 to 0.18, the 33 to 0.66. It turned all of those counts into proportions. But if you notice, just watch the shape of this curve as I click this button. Same curve. But what it's doing is it's actually being shifted. And the way it's being shifted is using those rules that I told you about manipulating. What we're basically doing is we're taking our old data, our old mean of 20, our old standard deviation of 0.0, or our old standard deviation of 3.46. And what we're doing is we're dividing it by 50. So what's going to happen is the following. We're going to go ahead, we're going to jump back here. Camera, zoom in. So now what's going to happen is, what does each dot represent? Each dot represents a proportion. So what happens now is I'm going to do everything divided by 50. And remember, our rules of division say that if I am going to take a distribution and I'm going to go ahead and I'm going to divide it by 50, what I find out is that the shape is unchanged. This is again back from our previous units. The center, the mean in this case, we're going to go ahead and divide by the 50. The standard deviation, which is the shape, we do the division by 50. So what I'm saying is that my original mean, when I'm talking about my count, was 20. It was that 50 times 0.4. My original standard deviation of the count was 3.46. Since I'm going to go ahead and I want to turn it into a proportion, I need to divide it by 50. So what I'm going to find out is that the mean of my proportion is going to be 20 divided by 50, which is 0.4. I'm going to find out that the standard deviation of my count is 3.46 divided by 50, which is going to be 0.0692. I want to show you something on this, because this one right here, it kind of makes sense. What ends up happening is, if you think about it, our original mean of a binomial was n times p. We're going to go ahead and we're going to divide it by 50, which is n. That's what we did. We did our original divide by n. Notice what ends up happening. Those n's cross off, and I'm left with just p. So the mean, when I turn that into a proportion, is whatever the claimed proportion is. So the mean of a sampling distribution of proportions is whatever the claimed proportion is. Now, we're going to do the same thing with this. We use the following formula to figure out the standard deviation, NP 1 minus P. What I want to show you is what happens. I'm going to divide this guy by n. Let's clean this up and make it look a little bit neater. So the way I'm going to make it look a little bit neater is I'm going to get everything under the radical. So if you think about it, n is the same thing as the square root of n squared. So what I can do here is I can rewrite this guy as NP, 1 minus P, over the square root of n squared. But if I have radicals on top and the bottom, I can put them all back together. I can do NP 1 minus P over n squared. And if you notice, this n up top cancels out with one of those n's, and I'm left with the square root of P times 1 minus P over n. And that is going to be our formula for a standard deviation. It's on the formula sheet, but I just wanted to show you the derivation of it. So that's kind of what I'm about to jump to. That's kind of what I talked about here. So again, our shape doesn't change. Our counts was approximately normal. Our proportion is also going to be approximately normal. So what ends up happening is I have a normal distribution with a mean of 0.4, a standard deviation of 0.0692. So instead of now having this curve where I'm doing it on counts of 20, I'm doing it on a proportion of 40%. Instead of having a standard deviation of 3.46, I have a standard deviation of the percentage. So by about 6.9%, a little under 7%. So now the question says, we know that a bag of Reese's contains exactly 40% orange. If we select a random sample of 50 candies, what's the probability that that sample proportion will be greater than 50? So the probability our sample proportion will be greater than 50. We draw our curve, 0.4 at the middle. I'm just going to go ahead and add my standard deviations at 0.0692. So about 47%, about 53%, about 60% roughly. I want to figure out what the area under the curve is. So I'm going to do normal CDF. My lower bound is 50%. My upper bound's lots of 9s because I want it to go on forever. My mean 0.4, my standard deviation 0.0692. When I break out the calculator, that tells me it's 0.0742. So there's about a 7% chance, a little over 7% chance that if I took 50 candies out of a bag, that I'd end up with more than half of them being orange. So I wouldn't be surprised. It's not significant. So that's where we're moving. So hopefully that kind of helps. So stop share. There'll be one more video that I'm going to do. It's going to kind of go over the practice that we do at the very end.